Hi gentlemen, women, femboys and furries. Welcome to the part 2 of network hacking for beginners. In today's video, I shall go over the different network protocols, their defenses, and their vulnerabilities. Before we start, it is good to understand what a protocol is. A protocol is just a set of rules that devices follow to talk to each other over the internet. It makes sure that both sides understand how to send, receive, and interpret data, kind of like how two people need to speak the same language or use terms that both parties will understand. I will explain the protocol name and what its purpose is so you can understand how the internet functions or depends on it. I will also explain its vulnerabilities, however only on a theoretical level. I will actually be teaching how those protocols can be exploited further on in the series. It is also really important that you watch the part 1 of my network hacking for beginners series so you understand what I talk about in this video. You may not understand this part or only understand it partially if you're missing knowledge that I went over in the last video. Anyways, this will be the last video which will teach you the theory and basics of networking as well as stepping in a little bit into the theory of network penetration testing, or network hacking in dummy terms. In the next video of this series, I will teach you how to set up a Linux environment as well as perform some basic attacks on your home network, whilst explaining how they work and why they work. So bear with me for the boring part, because theory is just as important as the actual practice. TCP/IP. Every network uses and functions on the TCP/IP model. This is how information gets moved across the internet. Let's talk about some abbreviations, what they mean, and how they structure the internet. As boring as this part may seem, I'll be throwing in simplified examples to make you understand. Internet protocol. Think of IP like the postal service, where information sent over the internet, like a message, a website visit, or a file, gets an address label with the source from which the information is coming from and the destination where the information should arrive, so your router knows where to send certain information, and when receiving certain information, knows where it's from. Your own IP address is almost like your home address. It is an identifier of your devices that connect to the internet. Your phone gets its own IP address, your PC, your tablet, and even a Minecraft server if you've ever set one up. TCP. Now let's talk about the protocols that actually transmit the data. This protocol is responsible for serving a reliable connection between two devices or services. It sets up a three-way handshake, which is used to ensure data that gets sent is not corrupted. When a TCP connection is made, both ends verify that they are connected via sending the SYN flag, then the SYN ACK flag, and finally the ACK flag. If you haven't guessed by now, the meaning of these flags stand for synchronize and acknowledge. In human terms, the handshake would look like this. Device 1 talks to device 2 saying, "Hello, are you there?" Device 2 replies, "Yes, I am." Device 1 confirms the response and sends the final message being, "Cool, let's exchange data." After everything gets confirmed, information starts getting sent in smaller bits of data, known as packets, which, as we've clarified before, have a source and destination address. If anything goes missing, the second party asks for a resend to make sure the information gets delivered intact, just like in a real conversation. If person 1 will not hear person 2, well, he will just ask again. This way, this protocol ensures a 100% reliable delivery of information. An example of this protocol being used would be sending an email over Gmail, for example. After setting up a three-way handshake, it ensures the email that gets sent will be intact and have all the information, and will not be delivered corrupted, especially if there is an attachment which would contain a lot of information, like a video file. The only issue in this protocol is that it is really slow because of the handshake. It is something that wouldn't be viable for things where speed over accuracy is needed, like in calls over the internet, for example WhatsApp or Discord, or watching live streams. This is where an alternative comes in. UDP. This protocol is the opposite of TCP. It has no handshake. It almost spams the other device with information, and whether the device receives it or not is not the sender's problem, as all they care about is speed of delivery, not accuracy. An example of this would be looking at live streams or calling others. It's pretty common for information to get lost, for a video to glitch for a split second, or for an online call to go silent for a bit. Those issues are often caused by slow connection, where your router or your bandwidth fails to keep up with the information that is sent. This can also be commonly found in video games, where you would teleport a bit, or where your enemies and bullets would start glitching right in front of your eyes too.
Have to get this off my chest. I'm telling you today that when I talk to you, oh, Cupid walks right through and shoots an arrow through my heart. And
So yeah, even though UDP is not always smooth and can be unstable like we saw in the previous clip, it's still better than playing in slow motion, like brutally slow. In conclusion, these are the two main lower-level ways of transmitting information: fast and unreliable, or slow and reliable. This is something that is mandatory for you to learn about, or well, you just did. Since we've already learned about a bit of the foundations, and this video will also explain some basic ways of exploiting protocols, it would only be fair if the first thing I explain is how a network can be taken down, while explaining the TCP and UDP protocol, as well as what are some downsides or defenses against those attacks. For this example, and all the other examples in this video, I will be explaining on how to exploit rather local networks, as that is most commonly the scope a network penetration tester can exploit within. UDP floods. A UDP flood is a type of denial of service attack that, well, denies service. The only use it has to a hacker is the ability to take down a network. The attack sends tons of random data to a target, trying to overwhelm its CPU and bandwidth. Since UDP doesn't need a handshake verified, it just blasts packets, trying to overload the device. The target gets overloaded receiving those packets, and often marking it as legitimate traffic or inspecting those packets. It's fast, but the effectiveness of it depends a lot on the device you're using to flood the network and the victim's hardware. What this basically means is that if you're using an old phone to perform a UDP flood against a really expensive router, you won't cause a denial of service, nor even be close to it, as the router is designed to handle massive amounts of data. Another way to prevent UDP flooding attacks would be to limit the amount of packets a particular user can send, and after a certain amount is reached, the overflow packets would just be dropped instantly without even checking whether they're valid or not. TCP floods. A TCP flood, mainly called a SYN flood, works differently. It sends connection requests with the SYN flag, but never finishes them. The target holds those half-open connections in memory, never finishing the handshake. If enough pile up, the server runs out of space in its connection table and blocks real users. This way, if the connection tables are set up incorrectly per user, this method can take down even high-end routers. Defense against the TCP flood would be as simple as the correct setup of the connection tables of the router. Nothing special here. Now, let's get onto the more advanced protocols that come in play after the initial connection. These protocols also bring way more use to a hacker, as they can compromise information, hijack login credentials, and get full control over the network. Please note that I will explain the simple attacks and defenses against them that can still be bypassed with more sophisticated methods, which is what I will be going over in further videos, like Keytrap for example, which critically affected and still affects the global internet to this day. Address Resolution Protocol. ARP translates IP addresses into physical MAC addresses on local networks. A MAC address is short for Media Access Control, which is the physical address for your network interface card. Basically another identifier, there's not much else to it. This protocol is mandatory to learn about, as it is often the starting point that leads to more things being exploited and hacked on the network. How it works. If you want to talk to a device, for example with the IP address 192.168.1.5, your device broadcasts a message to the devices on the network. Who has 192.168.1.5? Tell me your MAC address. The incorrect devices ignore the message, however, the correct device replies with its MAC address, or as we've clarified before, their local identifier, and then communication begins. During an ARP poisoning attack, the hacker floods your network with fake ARP replies, telling every device, hey, I'm the router. The devices that are connected, instead of sending information to the router, including sensitive information like login details or private documents, actually start sending it through the hacker's device first. Now all of the traffic is routed through the attacker first, letting them spy or modify data, causing a man-in-the-middle attack. Luckily, however, current encryption standards often mitigate those attacks. This is an attack I will be going over in detail in the next part of this series, as well as teaching you how to perform it. To protect against these attacks, enterprise switches and routers can track valid IP to MAC pairs and block any ARP replies that don't match, stopping poisoning attempts. Also, smaller scale networks can just hardcode IP to MAC pairs, so anything that is modified gets ignored by the devices and the router. Also, in more security requiring networks, like businesses, which often have their own security team, the security team can identify ARP poisoning attacks and investigate, as well as prevent these attacks. Also, as I've said before, current encryption standards often mitigate those attacks and interceptions too. Domain Name System. DNS is like the internet's phone book. It turns names like google.com into IP addresses. You don't type in IP addresses to visit websites. Instead, you type in names. DNS does the job of finding the correct address behind the scenes because, as we've learned before, each device or server exposed to the internet gets an IP address. A hacker can trick your computer and the router by making it use their custom DNS server instead of a legitimate one. That malicious DNS server gives you the wrong address, so instead of going to a real website like bank.com, for example, it sends you to a fake version that is controlled by the hacker that looks real. Even worse, antivirus software often doesn't check for DNS spoofing, meaning this attack can stay undetected and be performed flawlessly on smaller networks like cafe Wi-Fis or hotels. Defenses against DNS spoofing include DNSSEC, which is short for DNS Security Extensions, which adds a digital signature, like a stamp, to DNS replies, so your device can check if the answer is real and unmodified. It is basically like sending your friend a letter with a unique seal, where if the seal is broken, you know someone has tampered with it. Another way that is more simple is to use a VPN. A VPN hides your IP address and masks your internet identity, so that huge companies that sell your data cannot track you. A VPN also gives you more privacy and prevents you from certain attacks, primarily DNS spoofing ones. This is why our today's sponsor is Anyways, let's get onto the last protocol of this video, Dynamic Host Configuration Protocol. DHCP automates IP address assignments so you don't have to configure each device by hand. When your device joins the network, it broadcasts a message saying, I need an IP address, because as you know, devices need an IP address to access the internet. The DHCP server replies with an IP address that is specifically made for that device after making sure there is free space left on the network. The server also gives the subnet mask, gateway IP, and DNS servers to the newly connected device. Don't worry about the subnet mask part for now, although this is something you should have learned from the modules I listed in the previous video. A hacker enters the network and creates a fake DHCP server. He then tries to either overwhelm the router's legitimate DHCP server or reply faster with his custom server. This way, he controls the major service of the network, meaning the hacker can give out a fake gateway which starts a man-in-the-middle attack, although with a bit of a different methodology than an ARP poisoning attack that we've learned before, or his hacked DNS server and cause DNS spoofing, as well as some other things like control which devices get an IP address and which will be denied access. This way, the hacker practically gets control over the entire network. Defenses against those attacks would be DHCP snooping, which marks only the real DHCP server's port as trusted. Any DHCP offers from other ports are dropped, blocking rogue servers. In short, the solution is just setting up the network hardware correctly. I was initially planning to cover more protocols like HTTP, SMTP, which is email systems, and Active Directory, which is Windows networks. But after talking to a few people, I realized it would make the video too long and boring. I'd rather keep you engaged than drowning you in technical details. This brings up an important point. Cybersecurity is basically a never-ending rabbit hole. It operates in a constant cycle. Hackers find an exploit, while security researchers create a fix. Then hackers bypass that fix, leading to new defenses that get exploited again. Every defense vector I explained in the video still often opens up more exploits the hackers can take advantage of. It's like playing chess, but neither of the players are better than each other. Anyways, thank you all for watching this video. I'm currently testing new editing formats and methods, as you've noticed, so please tell me if there's anything that I could change which would make the video better in your opinion. In the next part of this series, I will show you how to actually perform these simple attacks that I've explained in this video.